So yes in the chat if you cannot, if you can see my screen. If you cannot see my screen, I say no. Okay, yes, very good. Let's go to the PowerPoint. Yes. Dang it. I forgot to fill out this. This is lesson 2. Okay, so today will be lesson 2 of our unit on functions overall. First, we're going to go over some homework, of course, and then we're going to go over the non-rigid transformation. So if you forgot last class, we went over rigid transformations. But today we are going over non-rigid transformations. We're also going over odd and even functions, and of course provide some examples too. So let's just get started with number 1 of the homework. This is one of the big ones that I really want you guys to understand, is finding domain. So remember, you need to find restrictions. The key point here is finding the restrictions on x. So that might mean like dividing by 0 or taking the square root of a negative number. Okay, so I'm going to give you guys like a couple minutes to put this in the chat, or if you haven't done this, please try this problem, and then we can start. All right, so let's go over this one. So William says 1/2 to 9 and 9 to infinity. Okay, let's see. So we do have a restriction here, which is x cannot be equal to 9 because you cannot divide by 0. So since you cannot divide it by 0, the denominator cannot be equal to 0. X minus 9 does not equal to 0. X cannot be equal to 9. That is the first restriction. But you also have to note that the domain of f also cannot include any x's that make the square root untrue, which means that you cannot have a negative number in the square root, meaning that 2x minus 1 has to be greater than or equal to 0. And if you solve this inequality, you can see that x has to be greater than 1/2. Therefore, our total domain is 1/2 to 9, union 9 to infinity. So good job, William. You got that correct. Let's move on to the second one. Find the new equation of k of x is equal to x squared if it is shifted right 6 units, reflected over the x and y axes, and shifted up 8 units. So find the equation for that. All right, so let's go over this. So we have a couple answers here. So that's good. Let's see what it is. So number 2 is find the new equation. So we know the parent function is going to be x squared, and we're going to be modifying this. So let's see, it is shifted right by 6 units. So let's just do that first. So since it is shifted right by 6 units, we have to remember the rigid transformations is, first of all, f of x minus c. That is a horizontal shift, which we are doing right now. It's reflected, which is either the minus negative f of x, or it's f of negative x is the reflections, and shifting up, which is a negative, well, no, not negative. It's a vertical shift. It's going to be f of x plus c here. So first we got to do the horizontal shift because the domain always takes priority. So x minus 6 squared. So remember, when you're shifting horizontally, it's kind of counterintuitive, because to shift right, you have to subtract something. But when you're adding something, you actually shift left. So that's the opposite way as a number line. So it's a little bit counterintuitive. So you have to remember to solve for the domain first. So when it's shifted, shifted right by 6, you're going to have to subtract 6 from the x here. And we also have that it's reflected over the y-axis, which is another domain shift. So that's going to be negative x here. Then we have also, it's shifted over the x-axis. So that's going to be another negative here. It's going to be shifted up by 8. So then we have k of x is equal to negative x minus 6 squared plus 8. So let's see. Yeah, that is correct. Okay. So are there any questions with this? If there are no questions, then I'll continue. Let's graph f of x is equal to negative x minus 2 squared plus 3. All right. So I'm going to give you guys a couple moments to go over this. All right, so let's go over this one. We have f of x is equal to negative x minus 2 squared plus 3. So who wants to volunteer to graph this one? Does anybody want to try this problem? Let's see here. Yes, William. Okay, William, how would I graph this?
So I just first found some points by plugging values in for x. So if x is 0, then y is -1. So one point will be 0, -1. And if x is 4, y is -1 also. So another point will be 4, -1. And if x is 2, y is 3. So another point will be 2 and 2 is 2 and 3. And if x is 1, y is 2. So a fourth point would be 1, 2, and a fifth point will be 3, 2. Because if x is 3, y is also 2.
Yeah,
Um,
this is very good. Okay, so basically what you did here is, this is parabola, right? Because it's squared. So we will learn about quadratic functions and the vertex form later this unit. So that's very good. So basically with the quadratics, there's an axis of symmetry and the points are reflected over this axis. So which is basically, so very good job, William. Not exactly the way I intended it to be. I'd rather you, for now, try to practice the transformations more because we'll learn specifically how to graph the parabolas later on. So let me just show you how to do it with the transformation. So of course, the parent graph is going to be looking like a parabola, right? And since there's a negative sign here, you already know that's going to be a downwards parabola. So we have this downwards parabola, which is usually like something like that. But first you got to pay attention to the shift now. So basically it is shifted to the right by 2, which and to up by 3. So basically the only thing that you really need to worry about right now is the vertex. The vertex is going to be shifted right by 2 and up by 3. So this is the new vertex, call it v prime or something. Yeah, so that's the new vertex, and you can draw your. My pen isn't working. Okay, let's shift this graph over here, maybe here. Okay, does it work now? Yeah, it works now. Okay, technical difficulty. Okay, now this is v prime. This is your new vertex, whereas your other vertex used to be 0, 0. Your new vertex, and a technique that we commonly use when we graph these modified graphs is we create a second axis. So this is x, this is y, this is x prime, this is y prime. And we create this second axis. And since these are all rigid transformations, meaning that it only affects location, but not the actual shape of the graph, the ratios are still the same. So as you can see here, like the ratios, how the graph works is still going to be the same. So we can just plot these points here. So after you determine the location of the graph, then I would plot points just to practice transformations, because sometimes you can't plot the points. It's going to be very complicated. So first figure out the location, then I would plot points to check your answer. Okay, so that's how you would I would graph. You can use this method or this method. They both work. So now let's go on to review some of the horizontal shifts and basically all the rigid transformations. This should not be too long. So we learned about horizontal shifts, which is f of x minus c. So this is very important because basically if c is, this is when c is positive, well, the graph shifts right. Basically, when C is, when you're subtracting C, the graph shifts right. And when C is negative, so instead you're adding a number, the graph shifts left. Okay. So let's see. How about let me go on Desmos for a second. What's on Desmos? I go to Desmos right now. Hold up. I'm going Desmos. It's gotta be the no, not the scientific one. The graphing one. Okay, so if I go on Desmos and it's basically a graphing calculator, it's let's say we are graphing the f of x is equal to f of x is equal to x squared. A very basic function. How do I? There's no. How about yeah, just x then, since I really can't do it. Well, a squared. Yeah. Okay, so x squared. Then let's hit enter and do something. F of x. Okay, we have f of x again. So let's look at the rigid transformations for the horizontal one. So for the horizontal one, if you subtract c, you can see that when c is positive, it's greater than 0, it shifts right? But when it's negative, it shifts left. So you have to remember it's a domain issue. If you go back to the PowerPoint, let's say it's f of x minus 2, right? So, and the domain is going to be, the domain, let's say for this imaginary function right now is 0 to 4. It's a common example, right? So when you subtract 2 from it, you have to plug in -2 into this inequality. And you can see by when you solve for x, the domain actually shifts right? You have to solve the domain first. That is why domain is priority. It's very important. Okay. If there are no questions, then I'd like to continue to the vertical shift, which is basically, it's not that tricky as the horizontal shifts. Honestly, it's just f of x plus c. It's directly affecting this y. It's literally adding something to the y. So it's very intuitive. When you add c, it's like it goes up, right? When you subtract c, it goes down, right? So when you have this, and you add 2 to it, it's gonna, it's gonna go up by 2. So it's very intuitive, unlike the last one. So if I add another slider here, f of x plus, let's say v. And as you can see, when it's positive, it just shifts up. When it's negative, it shifts down. So it's very intuitive here. Okay. So next, the reflections is also very intuitive. So f of x, we have 2 types of reflections. So basically, when the negative sign is outside of the f, that is reflection to across the x-axis. And it's basically reflected up and down. So you can have this turn into this, right? And this, when you have the negative sign within the f of x, that's a domain error. Well, not domain error, a domain issue again. It's, you got to solve for the domain, and you can see it's going to be reflected left and right. So if you have something like this, it'll turn into this. Okay, so that's basically all of our rigid transformations. Then I'd like to go over some of the non-rigid transformations, starting with the vertical stretch. So with the non-rigid vertical stretch, again, we need to know that non-rigid means it does change the shape. So with the rigid transformations, it does not change the shape. It changes the location only, but now it does change the shape. So let's go over those. Okay, so the non-rigid vertical stretch, basically, it's going to be f of x times c on the outside. And again, we are directly affecting the y here, meaning that it's, again, very intuitive. When c is greater than 1, you're going to be stretching. When c is less than 1, you're going to be compressing. So let's just write that down. So also note that this is in between 1 and 0, because when it's negative, again, it reflects, right? So you can have f of x here, but you can stretch it and you multiply it by like 1.5 or something. Or you can compress it when you multiply it by 0.5. It's all possible. Let's go to Desmos and try to model that. Okay, so, and then we have multiplied by d. And as you can see, we can have this, which basically stretches or compresses it vertically. You can see you can make it really skinny or very wide like this. And once you cross 0 into the negatives, you can see it reflects down and follows a similar trend like this. Okay, so now we can start experimenting with the horizontal stretch. So this one, whenever you hear the word horizontal, it's dealing with the x, right? And if it's dealing with the x, you have to deal with the domain. So this is another domain thing. And of course, it's going to be counterintuitive. So let's see, the horizontal stretch is going to be f of cx here. And we have a graph, which is the parabola here. Well, I guess we could. I don't think the parabola modeled it very well, actually. So let's go back to here and model it with something else, because this is very similar to a horizontal stretch. Instead, if we have something like this, you can see vertical stretch, something like this, or like this. Right. Horizontal stretch, if we use the same thing, it's going to become wider, like this. Yeah, or like this. Okay, so again, because it deals with domain, it's a little bit counterintuitive. If you have f of, let's say, 2x, and the domain is 0 to 2, the thing is, it actually the domain is going to be shrinking, because when you have 2x in this domain, x is going to be in between 1 and 0. So when c is greater than 1, well, you have to actually compress it. which is a little bit counterintuitive compared to the last one. And when c is less than 1, again, greater than 0, you actually stretch it. So when it's a fraction, you have to stretch it. So let's model that on Desmos. So you have this one, right? When it's greater than 1, you can see it actually makes it skinny like this. But when it's a fraction, as it gets closer to 0, it actually widens it like this. And of course, when it goes negative, it follows a similar trend. You can see. Okay, so you can see all of these transformations here. Yeah, okay. So I think that's it for the non-rigid ones, which is, yeah. For the non-rigid ones, yeah, that's all of them. So let's go over all of them. So we have the horizontal shifts. Again, domain is important. You have the vertical shifts. Domain is not important because it's affecting the y instead. You have the reflections. You have the non-rigid vertical stretch, the horizontal stretch, all of those. So now let's go over even and odd functions. Okay. So what are even and odd functions? So an even function is defined by functions symmetric with respect to the y-axis. And odd functions are functions symmetric with respect to the origin. So don't get confused or disoriented by this name, because it does not just mean that the power of the function is odd. So let's say you have a parabola. Yes, that is an even function because it's symmetric with respect to the y-axis. But when you have x to the third right here, it's not symmetric to the origin. So it's not going to be an odd function just because its exponent is odd. Okay. And how would you find out if functions are symmetric with respect to the y-axis or if functions are symmetric with respect to the origin? So one way you can see is by testing the symmetry. Basically meaning that when you're testing the even functions, to see if it's an even function, replace the x with the negative x and see if the function is still the same. So if you have a parabola and you replace x with a negative x, they're equal. It's still going to be the same. That's why a parabola is an even function. So an odd function, for example, would be x to the fifth. Well, not necessarily. Okay, maybe not x to the fifth, but I'm gonna have to think of one there. Maybe yeah, I don't know an odd function off the top of my head because all of these odd functions don't these functions with odd exponents don't really work as odd functions. So I'm gonna have to think of one of those. But anyways, an odd function, to find whether it's with respect to the origin, you're not just replacing one variable, you're replacing both variables. Both x and y. with negative x and negative y. Okay, so that's basically it. Yeah. Okay. So now, let's just see about, let's say y is equal to 3x minus 5. Well, obviously, this line is always shifted somewhere, right? It's like something like this. So obviously, it's not going to be an even or an odd function. And this shows us that if a function is shifted away from the origin, it's not going to be. It's not really going to be an odd function, because an odd function requires the function to be symmetric with respect to the origin, meaning it has to stay at the origin like this. Well, not necessarily, like this. It has to stay at the origin, and if it shifts away, then it's not anything. And it's just neither an even or an odd function. Not all functions can be classified as even or odd. Okay, so looks like we have a lot of time left. So I think we'll be ending class like 10 minutes early today at 5:50 EST. But let's just do some practice problems, and maybe I'll give you some more graphs to do later on. So first, let's just do this one. Determine if the function is even, odd, or neither. So I've given you two functions here, and you have to test whether they're even, odd, or neither. All right, so let's see. Okay, I think I accidentally closed out my PDF. Hold on a second. Let me get it back. All right, it's back. So let's go back to where we were. Yeah, okay, so this one. So we need to test whether this function is even or odd, right? So let's see, f of x is equal to x to the fourth plus 1. So remember what I said about testing even functions. We need to replace the x with negative x. So if you replace x with negative x, you're going to get negative x to the fourth plus 1. And you can see that it's still going to be equal to x to the fourth, because whenever you're taking the power, something to the power of an even number, it's always going to, it doesn't matter if it's negative or positive, it's going to be always positive, right? So it's still going to be equal to the original function, meaning that it is even. That's good. So we test even for this one. Obviously, when you have negative x to the third plus 1, this is not equal, meaning it's not even. And let's see if it's odd. So when you have negative y is equal to negative x cubed plus 1, well, if you want to compare it to the original one, which is something like this, well, you have to divide by negative 1, right? So y is equal to x cubed minus 1. So the thing is, the only difference between these is the minus 1. So it's not odd either, meaning it's neither. And if you actually visualize this, it's not going to be symmetric anyways. So are there any questions with this? So William, I saw that you got B incorrect and you said odd. So a lot of people make that mistake. So make sure you check before. And let's go on to example 2, which is to graph f of x is equal to 1/2 times x plus 3 squared. All right, so let's look at this. So we have the graph f of x, which is equal to 1/2 of a f x plus 3 squared. So we do have both non-rigid and rigid transformations in here, and let's see how we would do this. So this is basically modification of a parabola, and since it's positive here, we know it's a parabola that's opening up. So our parent graph should be looking like this. So we know that this parabola is going to be first shifted left by 3 units, like this, shifted left by 3 units, and then you're going to compress it vertically by a factor of 2. So we have this. This is the rough graph of our parabola here, which is not very good, right? So now we want to graph some extra points to see what our graph actually looks like. So let's just go with a table of values. Okay, so x and f of x. So when x is equal to maybe like -2 and -1, and then maybe like -4, -5. Okay, so when x is equal to -2, we have 1/2. Okay. Here, x is equal to -1. We have 2 here, and we have when x is equal to -4, we're going to have 1/2 again. And since there is an axis of symmetry here, we can say that these two sides, once you figure out one side, you can find the other side. So that is going to be the graph of our parabola. Are there any questions so far? Okay, if there are no questions, then I think that's gonna be it for today. Today's class wasn't that long. We mainly focused on the non-rigid transformations. We also added the even and odd functions in there because you'll be able to use even and odd functions in calculus. Those are quite important. You might use them, right? The even and odd functions. So I'm going to include one problem about even and odd functions in the homework. And I finished grading one class of the homework. I still have a couple more to go, but hopefully I got a lot of your grades in today. And then we talked about the rigid and the non-rigid transformations. So make sure you really know those, and make sure if you didn't take notes, you might as well take notes because they can be quite easy to forget. So make sure you're taking notes when you review, right? And that's gonna be all for today. I ended a little bit early today, 10 minutes early. So yeah, that's gonna be it for today. Now I'll post the homework shortly. Yeah, Kaylee, it's gonna be posted tonight or tomorrow, probably. Probably tomorrow. Okay, I'll see you guys next week.
Thank you. Bye.
Bye, thank you.
Bye.